Right, so now that we've gotten all of our housekeeping stuff done, today we're essentially going to go beginning to end and get through all the second order transient material. Last time we spoke about first order transients, single resistor, single energy storing element. That is represented, if we use our circuit equations, it'll be represented as a first order differential equation, which we use the form dx dt plus a x of t equals f of t, some sort of external force function. We learned that there was a way that we could solve this type of problem using essentially some, I don't want to say tricks, but methods from ENG212. Although we could have used Laplace, but we're not going to be focusing on Laplace in this class. So what's the next step? The next step is talking about more complex circuits that have more than one energy storage element. And so when we have circuits that look like these, R, L, and C, the system will be represented as a second order differential equation. So these are called second order transient circuits, or this will be a second order transient analysis. And so these two circuits here, we have a parallel RLC circuit that's sourced by a current source. And then we have a series RLC circuit that's sourced by a voltage source. And so these are going to be the two basic examples that we use, or structures that we use to tackle this problem. And the reason why is because we'll see in a couple of minutes, they yield a pretty similar system representation mathematically. And so we'll take both of these, it'll lead us to a similar type of equation, and then we'll talk about how to solve that equation. And then next time when I post the video lecture, I'll put up an example of how to solve a second order transient physical example or a practical example. All right, so jumping right in here. So we have two different circuits. And we want to start off by describing their behaviors using Kcl and Kvl respectively. We're going to start off by talking about the equation on the left, the circuit on the left. Single node pair. When we have a single node pair, the voltage is the same across all of the elements, so it's not very interesting to talk about the voltage across them. But the current through all the elements is different. So we're going to use Kcl in order to discuss what's going on. So we know that Is is equal to the sum of all three of the currents that are running down along the individual elements. IR, IL, and IC. So that's shown right here. We can substitute in for those values using Ohm's law. And then the VI, differential VI relationships between voltage and current for the inductor and the capacitor. IC is equal to C dVc dt. IL is equal to 1 over L times the integral of Vc dt. Now, you'll note that I call all of them Vc because the voltage across the capacitor is the same as the voltage across all of them. And so later on, I actually just get rid of the C and I just call it V of t. That's the voltage across the entire node pair. So what do I do going from here to here? Well, essentially nothing. Actually, we just rearrange the terms. And so what we end up with is Is of t equals Vt divided by R plus 1 over L integral of Vt plus C dV dt. And so this describes the behavior of the RLC circuit. Why is this called a second order differential equation? Is because, the difference in the orders of the derivatives is 2. You can consider this to be a -1 derivative, an integral. So we have 1 minus a -1. And later on, we'll see that we can actually get rid of the integral. We'll take the derivative of the entire expression, which will make the second order nature more evident. Okay, so far, we are just applying things, a combination of Kcl and expressions that we're already familiar with. Nothing new there. Next, our series circuit. So for our series circuit, I'll try to leave as much on the screen as possible. For our series circuit, we have Vs is equal to the voltage across the resistor plus the voltage across the inductor plus the voltage across the capacitor. We'll substitute in there using Ohm's law as well as the VI relationships again for the inductor and the capacitor. I, L times R, L di dt, and then 1 over C, the integral of I, L dt. Again, I, L is the value we use for all of the currents because the current through the inductor is the same as the current through all of them. And you'll see in a second, we can just call all of them I of t, which represents the current flowing through the entire circuit, the loop. So that's our equation. Let me pause for 1 second and give everyone a chance to catch up. All right, to make these equations look a little bit nicer and to, let's say, meet the form that's, sure, yeah. Is that good enough? Yeah, that's good enough. All right. So to make these equations look a little bit nicer, say it again. Never mind. I'm going to post the notes online. So honestly, I think there's a lot of writing in these. So I would pay attention, try to scribble down as much as you can, but I'm going to post it all. The video will be online. So maybe trying to copy it, letter for letter, word for word, it might be a little difficult this time. So to try to make these look a little bit nicer and to meet the form that is generally used for these types of differential equations, we're going to take the derivative of both sides of the expression. So what ends up happening is that our integrals will become just the base function. And so because the derivative of this term right here will leave us with 1 over c I of t. Right? The derivative of an integral, if they're with respect to the same variable, it just gets rid of the integral. And then our quote-unquote regular function will become a first-order derivative, and our first-order derivative will become a second-order derivative, right? So for the series circuit, which is the one we have right here, what we'll have is L, second-order derivative of I, plus R, first-order derivative of I, plus 1 over C times I. And we can't forget that we have to also take the derivative of the source that's being applied. This right here is doing the same thing to the parallel equation, parallel circuit expression. So now, why do we do this, okay, besides the fact that this is the general convention and the way that it's displayed? Because we see that both of the circuits yield a second-order differential equation with constant coefficients. They have the same form. Okay? The values may be different. The value of f of t is different, and the coefficients themselves are different, and the state variable is different. One uses v, one uses I. But the form is the same. And it looks like this right here. Second-order derivative of our state variable plus a constant, which we'll call a1, times the derivative of our state variable, plus another constant, a2, times our state variable equals some sort of external force being applied. So if we were to compare this to this up here, first things first, we would have to divide everything by c, because in our form, the second-order derivative doesn't have a coefficient. So what would a1 be? A1 would be 1 over RC. What would A2 be? It would be 1 over LC. And what would this f of t be? It would be dis dt. And you can do the same thing for the second equation. So now what we're going to do is we've taken both of those circuits, we've shown how they can be represented by the same equation, so let's figure out how to solve that equation. If we can solve that equation, we can solve both of the circuits that we just discussed. Now, This is not a course that's focused on transient analysis. As we get to more and more complex circuits, the expressions will get more complex, and the analysis will potentially get more complex. So I don't expect for you to walk away from this class feeling very confident about doing a transient analysis on any second order circuit that you can think of. Okay, let's keep it within the bounds of what we're talking about in this course, which is a circuit similar to this or with very few changes with respect to this. And you'll see this is also reflected in the homework, okay, in the way that the homework is structured. So how do we solve this? So the question remains, how do we solve this second order differential equation? And we're going to use the steps that are shown below. So first thing, we are going to draw upon many of the lessons, or let's say, ideas that we also used for solving first order differential equations. And one part of that is this idea that we can split the solution again into our complementary and our particular solutions. And so we're going to do that. Step 2. Again, we will assume that f of t equals a constant. And so the following will apply. Okay. So if we take the form up here, that's what we say, that's what we mean when we say so we're taking this form and we are using it down here. And we are going to plug into this equation. We are going to plug into this equation two things. We are going to assume that f of t equals a constant. And if f of t equals a constant, we also said last time that meant that our particular solution would be equal to a constant as well. So those are the two substitutions that we're making here. If we plug in xp equals k1, we have second order derivative of k1 plus a1 derivative of k1 plus a2 k1 equals constant. Anything that's a derivative of a constant will go away, right? So what it does is it reduces our second order differential equation to just an algebraic one. We have a2 k1 equals the constant a. So we have this right here. This is the exact same process we used to solve for the particular solution in the first order transient. And because it's based on this idea that we're getting rid of the derivative components, it actually works in the exact same way, right? For the first order differential equation, the solution was k1 equals uppercase A over lowercase a, because we only had one coefficient. And this one we have two coefficients, and so instead of it being called A, it's called A2. Okay, so this right here at least tells us the form of our particular solution. So that's half of the battle. Okay, now moving forward, we still need our x sub c. That's what we're missing. So let's turn our attention to the homogeneous equation below. And when I say homogeneous, right, that's exactly the same as the equation that we had before, except now we have gotten rid of our f of t. That's the only, yep. That is the only difference, is that we have gotten rid of our f of t. Same form. And so to make this easier to say, because I'm tired of saying second derivative of x, you can also call this right here, sometimes we call this x double prime. That's just second order derivative, x prime. So I'll just make it easier for me to talk because I'm getting tongue-tied. All right, so x double prime plus a1 x prime plus a2 x equals 0. What we're going to do here now real quick is we're going to make a substitution that is going to help us illustrate something later on. It has nothing to do with the derivation. It's not going to help us with the derivation. So I'm going to call a1 this right here. I'm going to replace it with some other values. And these values have physical meaning, practical meaning for the solution when we do get to that point. So we're going to say it's equal to 2 zeta omega 0. Omega 0, actually in a second we're going to talk about what the meaning of those constants are. But we'll just refer to them by the symbols for now. So a1 is going to be 2 zeta omega 0, and a2 is going to be omega 0 squared. Just because both of these use omega 0 doesn't mean that they are inherently related in any way, because we have zeta, that's an additional degree of freedom. They can have any relationship between them that is dictated. It's just another way of referring to a1 and a2. Does that make sense? And so if we rewrite this equation up here as shown below, now we have x double prime plus this weird looking coefficient x prime plus this other weird looking coefficient x equals 0. We're still solving for a1 and a2. It's just that we have already given these a1 and a2 values some sort of more meaningful definition. Okay. So we're still trying to solve the the homogeneous equation. From the lessons that we have learned in the previous section, we know that x sub c must have the form of an exponential recovery. Okay? We're still going to have x sub c equals some constant e to the st. The problem is we don't know what this other constant is, and we don't know what s is. So the second order differential equation, the objective is going to be a lot like the objective for the first order. We generally start off knowing the form of what it is that we're trying to find. We're still trying to figure out that form here. But once we figure out that form, the problem becomes solving for the coefficients, not solving for the entire expression. Right? In the first order problems, we had to solve for our tau, which is related to s. We had to solve for our k1 and our k2. These problems are going to end up working in a very similar way. We're going to get a form in like 5 minutes, and then the problems are going to be associated with trying to solve for the coefficients. Okay, so what happens when we take this form right here and we plug it into the equation that's right there? So when we take the second order derivative of k e to the st, we end up with s squared k e to the st. Right? Because you can think about it here. If we take the derivative of k e to the st, it gives us s k e to the st. If we repeat that again, it adds another s. Every time we take the derivative, it pulls out another coefficient, so it keeps pulling out more and more s's. So this is first order derivative, and this leads us to the second order derivative. When we plug in for x, that's just the solution itself, k e to the st. So we plugged it in 3 spots. We plugged it in here, we plugged it in here, and we plugged it in here. Same thing as you would see here, here, and here, right? And after we take our derivatives, we end up with something that looks like this. All right. Now for the first order differential equation, there was one way that we could use to get the coefficients. That This is really where the first order and the second order branch off from one another. We can't use that technique here because now there's more coefficients that we have to solve for. So we need something that will allow us to address the higher order. So let's take a look at this equation for a second. It's equal to 0. So that means we can divide or multiply by anything that we want to. All three of these added components, they are all multiplied by Ke to the st, right? So if I wanted to, I could just divide by Ke to the st, and it would get rid of that, it would get rid of that, and it would get rid of that. They would all go away. And what we would be left with is this equation right here. So this is a form of this without the Ke to the STs. This is called the characteristic equation for the system. This is definitely from when I used to teach ENG212. I remember we definitely touched upon this. So characteristic equation sounds familiar? Yes? Okay, at least one. Some better than usual. So we have s squared equals a1 times s plus a2. Again, a1 is 2 zeta omega 0, and a2 is omega 0 squared. So now we can talk about what these values mean. Omega 0 is the undamped natural frequency of the system transient, which is going to be the frequency at which the transient oscillates. And so what we see is that for a second order transient, we no longer always have this exponential response that settles quickly and is always moving in the same direction. Second order transients can oscillate. And then we also have the exponential damping ratio represented by zeta. And so that is the damping term, right? You've all discussed oscillations in some class at some point, and so you're familiar with what damping refers to, right? It's the rate at which the oscillations die. So, now that we have our characteristic equation, you can see this is a second order polynomial, right? It's the same as x squared plus 4x plus 4. So the next step in this process, step number 6, is to see if we can use the quadratic equation to solve the characteristic equation above for the value of s. And so what we see right here is this is our quadratic equation, which can be used to solve something in the form of as squared plus bs plus c. If we take that implementation and apply it to the characteristic equation, where, for example, b is 2 zeta omega 0, a is equal to 1, c is equal to omega 0 squared, we end up with the solution that's shown here, which is minus zeta omega naught plus minus omega naught times the square root of zeta squared minus 1. And so this gives us the values of S1 and S2 for the differential equation. Now, step number 7 becomes a little bit complicated. So the complementary solution will be composed of some combination, some linear combination of ES1t and e to the S2t. Now, the version that's shown right here is actually that which will, if we scroll down for a second, that which will apply for what we call the overdamped case. However, this form right here, again right here, is not necessarily going to be the form that's going to apply to every type of solution. We also can't forget our particular solution if we do have one. So I also took the liberty of renaming these to K alpha and K beta because I thought it might be confusing using the numbered indices again, calling them K2 or K3. Okay, so like I show right here, both of these steps, step 7 and step 8, are assuming that we have what is called the over-damped case. So if we have this type of complementary solution here, you see that we can set it equal to the initial condition as well as the initial rate of change for the state variable and solve using this matrix form right here. That'll allow us to come up with K alpha and K beta. And so that would essentially complete the process. But we still need to address another question, which is what effect does the damping case have on the actual system response? And probably the more important question is this one right here. What are the different forms of the complementary solution? Again, the one that we showed here is only one of 3 potential forms. So for the overdamped case, the natural frequencies S1 and S2 are real and unequal to one another. And that's a side effect of the value within the square root here being greater than 0. Therefore, the response will have the following form below. This form is essentially just what we showed above. K alpha e to the S1t plus K beta e to the S2t, where the S1 and the S2 values are defined as zeta omega 0 plus square root of zeta squared minus 1. This is highlighted in the purple. The natural response, therefore, is the sum of 2 decaying exponents. So the overdamped case exists when zeta is greater than 1. And again, if zeta is greater than 1, then what we have underneath this square root will be greater than 0. Next case. What happens if zeta is less than 1? The underdamped case. When zeta is less than 1, the value here underneath the square root will be negative. And so what that means is that the values of S1 and S2 will be complex, as shown here. Our S1 and S2 values have a J in them. There's the more descriptive version here. There's also a simplified version right here where we call the real portion sigma and we call the imaginary portion omega d. Now the problem is that we can't take these roots and represent them in this type of form here. The reason being that for a physical system, the e to the something imaginary t, right? How are we going to translate that to a physical voltage at time t? Now, in order to address this, we're going to use a conversion that we should have all seen in ENG212, which allows us to convert an exponent to that has a complex power to a cosine and sine based expression. So we take this and we convert it to this form down here. So what we end up with, and this form, as you will see, has no complex values, no imaginary values within it. Xc equals e to the negative zeta omega t times a alpha. This is one of the constants we'll need to come up with. Cosine omega naught times square root of 1 minus zeta squared times t plus, and then the same thing for the sine. And so what we'll have to do is we'll have to solve for A alpha and A beta instead of K alpha and K beta. But the way that we would do this would be very similar to that shown right here. Again, what we would do is set this equal to x to the 0 as well as dx0 dt, and use those two expressions in order to solve for our A alpha and our A beta. The final case that we're going to look at is critically damped. And critically damped addresses the case where zeta is equal to 1, which means that we won't have two roots. We'll have a repeating root. Both will be equal to negative zeta omega 0. Now, you may ask yourself, well, why can't I just have beta alpha e to the negative s1t plus b beta e to the negative s1t? Why can't I just write it two times? What that would result in is we could combine these two together into a single value, and we would end up with a first order transient response to a second order transient problem, which is problematic. Now, I believe this topic is discussed in more depth when you review method of undetermined coefficients in ENG212. But without going into details, the solution to this problem is to create a second term which adds a coefficient of t. So what we have is b alpha e to the negative s1t, b beta e to the negative s1t times this additional t. And what that does is this provides us two separate terms, and a second order response to the second order problem. So essentially, when we branch off from this step right here, step number 7, we have to jump down and look at the three cases, case 1, case 2, and case 3, to determine what the form of the solution should be, and then use that form in order to solve for the unknown coefficients, which are called K alpha and K beta, A alpha and A beta, or B alpha and B beta. Now, the last question we're going to address here is, what do the damping related terms mean for a practical or a physical response? The first one we'll talk about is critically damped. In the critically damped case, we will see this second order response, and the peak and the decay will be the fastest. The overdamped case will have a similar shape, as you can see, moving one down. However, it will be slower to peak as well as slower to decay. The one that takes on a very different shape is the underdamped case, where if you go back up and look at the math, what we'll see is that there are the cosine and sine components, which means we can expect it to oscillate. So what you end up with is this exponentially damped sinusoid that decreases with time. And why is it exponentially damped? Because the cosine and sine components have a coefficient of e to the negative something t. Anyway, this is an exponentially decaying value. And so next time what we're going to do is we are going to dive into some more examples regarding second order transients and discuss how to solve one practically, going from A to Z and discussing all the details.